Hello everyone, welcome back to the course on measurement and instrumentation, and we are in the 5th week of our discussion. We are discussing the second module of this course, which is about analog meters, and we are going to start today a new kind of instrument as promised in the previous week, which is electrothermic instrument. Okay, so let's see that how this electrothermic instrument can be used to measure some electrical parameters, for example, say current. Okay, so before we actually jump into the torque equation and how we can use this for the electrical measurement, let's try to have a generic view about this electrothermic instrument. Okay, so electrothermic instrument, as the name suggests, depend for their indication on some property of a circuit element which is heated by, or there is some thermal data produced by flowing current. It can be simply heat or it can be a heat flow. Okay, so let's try to understand this from different view. Okay, so these electrothermic instruments are used for the measurement of current at higher frequencies without any significant errors, because we'll see that in most of the electrothermic instrument, frequency of the signal plays a little role, and it is more about how much heat it is generating. Okay, so if you see, in fact their main field of application is the measurement of current of frequencies above the range of the other instrument that we have already covered, like moving iron kind of instrument, or say the transfer instrument that we have seen, the electrodynamometer kind of instrument. Okay, so at moderate frequencies, they can be used for very precision measurement of say current or voltages. Okay, so there are basically three different type of electrothermic instruments. So these are based on three different electrothermic effects which can be utilized for measurement of current, and accordingly there are these three different electrothermic instruments. There are one or two more electrothermic instrument which is beyond this the scope of this course. Okay, so like we have hot wire instruments, which is very important for us, and we will try to understand this particular kind of electrothermic instrument in today's class. Okay, apart from that, we have two more kind of electrothermic instrument, like we have a thermocouple instrument, we have bolometers, etc. Okay, so our main goal today is to understand the hot wire kind of electrothermic instrument. Okay, so as the name suggests, hot wire instrument works on the principle that the current passing through the coil, or say a simple wire, increases the length of the wire. Okay, so because of this heat which is being generated because of the resistance of the wire, there is certain amount of heat that is generated. Okay, and this wire is expanding because of this heat. Okay, so this is the generic principle of these hot wire instruments. Okay, so the wire through which this current is flowing regains the shape with the help of a control spring, and the expansion, and when you decrease the current or when you make it zero, it contract. Okay, so the expansion and contract of the wire will be used to deflect the pointer of this particular meter. You can expect that the deflection will be not very high, because there will be only a slight change in length. It will be not very much significant. So you have to utilize certain mechanism to convert this translation motion, because this wire is expanding, okay, or contracting. So you have to translate this motion into certain angular motion. So we'll see that in the construction, that how this translation motion can be converted into a angular motion. Okay, so when say current I flows through a wire of say resistance R, okay, for a particular time, like certain time, say T, according to the Joule's law, the heat produced in the wire can be given by this equation 1, which says that the heat flow H is equal to I square RT, where I was the current which was flowing through this, right, and R is the resistance. So I am calling this as equation 1. All right. So if the wire, for example, has a mass of m and the specific heat is C. This heat that is being produced in this wire will raise its temperature by delta T, and this H can be given again by equation 2, which is like H is equal to mc delta T, which is the temperature changes. Say initially it was, say it has reached to T2, so initially it was T1, so it is basically T2 minus T1, right? So this is the second equation of this heat. So we have seen that H is equal to I square RT, and this H is equal to mc delta T, okay? So what I can do easily is I can equate them, because both are actually heat represented by different parameters. So I can write simply like I square RT from equation 1 is equal to mc delta T from equation 2, okay? I am calling this equation 3, and if I simplify it and find the value of delta T, I will get simply I square RT divided by mc is the change in the temperature, and I am calling this as equation 4, okay? So the change in the temperature is nothing but it is equal to I square RT divided by mc, okay? Therefore, this temperature, if you see, or the change in basically this delta T, change in temperature is basically directly proportional to the I square value. Of course, I am assuming that this R is fixed and this current is flowing for a fixed time T, and M and C are constant, okay? So M and C, we have seen that C was the specific heat and M was the wire's mass, okay? So this change in the temperature is directly proportional to I square, okay? This is a very, very important relationship for the hot wire instrument, and this is the foundation on which this instrument is built upon, okay? Now let us see that for a wire of say initial length L, and the linear thermal expansion will, if you know, the delta L will be given as alpha L into del T if I am ignoring the higher orders, okay? So here alpha is the coefficient of linear expansion, right? And L was the initial length, and this delta T was the change in temperature in this particular equation 5, all right? So delta L is equal to alpha L into del T, okay? Now substitute this delta T from equation 4 in this particular equation, okay? Equation 4 has given me this delta T value as I square RT by mc, all right? So if I substitute it, equation 6 will be delta L equal to alpha L into del T, and del T from equation 4 was I square RT by mc. So delta L can be given as alpha L into I square RT by mc, okay? Now if you see this equation 6, from this delta L can again be written as value which is proportional to I square, okay? Of course, I am considering this alpha is constant, okay, and this R, T, M and C and L are fixed values, okay. So for this, delta L is directly proportional to I square, or change in this length is directly proportional to square of the current flowing through this wire, okay. So the increase in the length of the wire, delta L, is equal to the square of the current which is passing through it, okay. So this is a very important relationship for the hot wire instrument, okay. If you see, unlike magnetic instruments, their operation is basically independent of the current direction, okay. We have seen in the previous cases that when current is changing or direction of current is changing, flux values or flux direction is changing, okay. We have seen all those things, okay. But in this case, this is independent of the direction of the current, and this is also signified from the relationship delta L is directly proportional to I square, okay, in place of I, okay. So therefore you can say that like other instrument where we have seen the parameter or deflection is directly proportional to I square, this kind of instruments are also suitable for both kind of signals, be it AC or be it DC. Depending on type of signal, the heat will be generated by that particular component. So like for DC it is the IDC value, and for IAC it is the RMS value which is causing this heat, right. So I think the basic principle is clear to us. I will just overview it once more so that it is very much clear to all of us. Okay. So hot wire instrument, as I have mentioned, that they work on Joule's law of heating. Okay. So H is equal to I square RT, where H is the heat produced and I and R as the current and resistance of the wire, current flowing through the wire, and R is the resistance of the wire, and T is the time duration in which this heat is flowing. We have already seen this equation. Okay. So we have seen also that when current flows through a thin wire, please note that in this case the wire is very thin and the thickness is very uniform. Along with the thickness of the wire, the uniformity of the thickness is also very important to keep this delta L parameter constant throughout the wire's length. Okay. So we have seen that when current flows through thin wire, heat is generated due to its resistance value. Okay. And the temperature rise causes a thermal expansion of the wire, the delta L value, and this expansion can be utilized to convert into certain mechanical displacement. Okay, then this mechanical displacement can be responsible for the movement of the pointer. All right. So what basically we are doing is we are trying to sense the current indirectly. First, this heat is generated in the wire, and because of that there is a certain expansion. So it is kind of indirect way of measurement, but of course we are seeing the deflection directly on the pointer. So we are not classifying them direct or indirect way. Okay, we are just understanding this in the way that how this pointer is moving. So this movement although looks very direct conversion of the current into the pointer movement, but it is basically the mediator heat which is responsible, or the change in the length of the wire which is basically responsible for this pointer movement. Agree? Okay, so let's try to understand the working principle or working of this hot wire kind of instrument. Okay, so the basic principle we have already understood. Okay, in this hot wire instrument, the current to be measured is passed through fine wire, which is basically a alloy of platinum iridium mostly. So I am talking about this wire. I am using a word continuously hot wire because this is the wire through which the heat has to be flow down. Okay, so this has to be stretched between two different terminals. Okay, a second wire, which is basically made up of a regular phosphor bronze wire that we have already seen in the PMMC kind of instrument. Okay, is stretched, is attached to, say, I am calling this, say, X and Y point. So it is attached at some point, say at Z. Okay, so a second wire which is made up of phosphor bronze wire, which doesn't have to be a platinum iridium wire. Okay, is attached to the this thin wire at one end and to a terminal at the other end. Okay, now we have a thread basically made up of mostly silk is attached to this second wire. Okay, this thread basically passes over a pulley and is fixed to a spring. This pulley and the thread kind of arrangement is very important to convert, or say basically I would say magnify the expansion, which is very less, the expansion of this wire, the hot wire, okay, on a scale. Okay, so this will amplify the mechanically the movement of this pointer. Okay, so this thread passes over a pulley and is fixed to a spring, right? So when the current is passed through the fine wire, it gets heated up, and as usual it will expand, as we have already discussed in a thermal coefficient section. Okay, the wire is magnified and the expansion is taken up by the spring basically. Okay, so this causes the pulley to rotate and the pointer to deflect, indicating the value of the current. So if you see, the expansion of the wire was kind of translational motion. Okay, but that is being converted into a rotational motion. Okay, or the angular motion of this pointer. All right. The expansion is basically proportional to the heating effect of the current, and hence to the square of the RMS value of the current, as we have already seen that the delta L is directly proportional to I square rather than being proportional to I. Okay. Therefore, the meter can be calibrated to read the RMS value of the current, be it a sine wave or any other AC signal. Okay. So, the deflection is related as like theta is related to or is directly proportional to the expansion delta L. Okay. This is directly proportional to delta T, which is in turn proportional to I square. Therefore, the deflection is directly proportional to the square of current or I square. Okay. So, this is also a square, I mean this kind of instrument also shows a square law characteristic and can be classified as a square law instrument. Okay. So, let us see the construction of this hot wire kind of instrument. The main components of this hot wire instruments are hot wire itself. So, hot wire element like this is the basic building block or basic component of a hot wire instrument. Okay. It has a fixed support, something like this. Okay. You have a tension spring. Okay. And we have a silk thread, sometime also known as linkage. So, linkage is nothing but a thread of silk or any other non-conducting stretchable material. Okay. And then we have a pointer and a scale arrangement. Okay. So, this is the basic construction of a hot wire instrument. Okay. Let us see them in very brief, that how they looks and what property they should possess to basically work or function properly to measure the current or voltage which is under measurement. Okay. So, first is hot wire element. Okay. So, this hot wire element, as I have already mentioned, that it has to be very thin and uniform thickness of platinum iridium alloy. Okay. Because it has high resistivity, it has also very high melting point, and the temperature coefficient of resistance is low for this kind of material alloy. Okay. Also, this high melting point and this alloy behavior is such that even at elevated temperature, it does not get oxidized. Okay. So, because if you have even a small oxidation of this wire, what will happen is basically the temperature coefficient of resistance for the thin oxide layer at the wire and the wire itself will be different. Okay. So, there will be always a chance of having erroneous result. Okay. So, therefore, this platinum iridium alloy is mostly preferred for this hot wire kind of instrument. Okay. The second important constructional part of this hot wire instrument is the fixed support. Okay, which is basically used for pushing this wire or putting this wire at a rigidly fixed position. Okay. To provide basically a stationary support, so that this one end is not moving at all. Okay. Then we have a tension spring. So, the other end of the wire, which is already hinged at one position, okay, is connected to this particular spring. Okay, and this spring maintains the tension and provide the restoring force, basically used as a controlling system. Okay. Then another important thing in the construction is the silk thread, which is also known as linkage. Okay. This although looks very mechanical in nature, it connects the spring to the pointer itself. Okay. And therefore, if you see, it converts the linear expansion of the wire into a angular motion. Okay. So, the pointer and scale system is very simple. The pointer moves over a calibrated scale, and the scale in turn is a non-uniform scale, because the current is directly proportional to I square rather than being proportional to I. Okay. So, the scale characteristics are very simple. Scale is non-linear, means that since it is directly proportional to I square, it is crowded at lower. So, the scale is something like this. Okay. And it is narrower at the or more open basically at the higher values, and at lower value it is very much crowded. Okay. So, this is all because the deflection is directly proportional to I square rather than proportional to current. Okay. The damping is basically provided by the air friction only. Okay. So, air friction damping is there, which makes the system little sluggish. Okay. Eddy current damping cannot be provided here because there is no magnetic field. Okay. So, when there is no magnetic field, there is no mean of having eddy current damping. Even if you try to provide eddy current damping by providing external, say, metal sheet, okay, where the eddy currents can form, but the problem will be it will make the system more bulky and may not be that helpful because you are using silk thread, which is again non-conducting in nature. Okay, so eddy current, there is no chance of having eddy current damping, and mostly it will depend on air friction damping. Okay, therefore the response is slow. Also, there are other ways to explaining that why these systems are very slow, and one of the understanding is like we have to rely upon heating and cooling of the hot wire. Okay, and the process of heating may be a little faster, but the process of cooling is not that fast, and you have to have external arrangement if you want to have a quick recovery from the heated wire. Okay, so the thing is their response to the system is very slow, and they will not provide you very fast response as well as recovery for the current measurement, for example. Okay, now we have understood the working principle as well as its construction. Now let us try to quickly understand the torque equation of this system. Okay, the mechanical arrangement that we have just seen, you have silk thread, pulley, spring, so on. Okay, the converts the elongation in the wire, the delta L, the expansion, into the torque, and therefore the deflecting torque is equal to, say, or is directly proportional to I square, and TD is equal to, say, S into I square if I replace this proportionality with certain constant. Okay, so in this case, if you see this S, okay, I am calling this, say, equation 7. Okay, this S is a constant and depends on several factors of the wire, like what material this wire is made up of, what is its length, what is its thermal properties, and what is the mechanism of being expanded. Okay, so the deflection torque can simply be given by this equation 7, where TD is equal to SI square. Okay, now the controlling torque is provided by the spring. Okay, and say spring has a spring constant K. I am calling this as spring constant, as we have already seen in the previous cases also. In case you are coming to this lecture directly, this will help you. Okay, so in this equation, say K is the spring constant, so TC is equal to K theta. I am calling this equation 8. Equation 7 and equation 8 can be equated under steady state condition, and in that case this K theta is equal to SI square, and theta is equal to SI square by K, or theta is basically proportional to I square, or the deflection is directly proportional to the square of the current. So irrespective of what direction your current is flowing, you will have a deflection. All right. So let's see what will be the effect of temperature on this particular kind of tool. Okay, particularly because of ambient temperature. I mean, temperature makes only one kind of source of error. There are other sources of error, like because of mechanical fatigue of the wire, edging of the material, overloading of the wire, as well as calibration drift. But let's see this ambient temperature error first. Okay, so this is like if, say, your instrument is kept inside a wire. Ideally it is expecting that it will behave, say, in room number A and room number B in the similar fashion, because the user is not aware that your device is very much vulnerable to the temperature. Okay, so change in room temperature of course affects the wire expansion, because this wire is very sensitive to the change in the temperature. Okay, and this will cause a zero shift as well as a scale error in case of this kind of instrument. Okay, and this is known as ambient temperature error. Okay, so there are some ways to compensate it, like by using dumbing wire, by using dummy wire, by using special alloys in this material of this wire. Okay, and then there are some mechanical design where you take into consideration the temperature compensation in itself only. Okay, so the sensitivity of this device are, in our opinion, is not very high. Okay, sensitivity is poorer because the expansion is not very high, and then that linear expansion has to be or translational expansion, you can say, in more mechanical term, has to be converted into this angular expansion or angular movement of the pointer. So sensitivity is not very high, and therefore not suitable for very small currents. Okay, but this instrument has better accuracy at elevated currents. Okay, so talking about the frequency independency of this instrument, heating effect does not depend on the frequency we have seen. Okay, they are suitable for high frequency application like for AC and RF measurement, and they are commonly used in radio frequency current measurement. Okay, so this device can work for both AC and DC. So same deflection for AC and DC is possible at RMS value, and they are basically true RMS responding instruments. Okay, the advantage of using this kind of hot wire instrument is like can be summarized from our previous discussions, like they can measure both AC and DC as we have already discussed. Okay, they have the capability to have a true RMS measurement, and their behavior is basically frequency independent, and that's why we have talked like this can be utilized at higher frequencies. Okay, the construction is very simple. Okay, you have this pulley and silk thread arrangement. Okay, and this hot wire also is very simple. So the construction is not very difficult, and they are also suitable for non-sinusoidal waveform. Mostly the analog instruments are more suitable for sinusoidal waveforms, but then hot wire instrument only take into consideration the heating effect, and that's why the heat is coming from sine wave or cos wave or a square wave or triangular wave. It doesn't matter for this kind of instrument. It will just convert the RMS value of the current into heat. Okay, so they are suitable for non-sinusoidal form of signals as well. Okay, however, there are certain disadvantages, like it has a very thin wire. Again, that wire will be heated also because of this heat flow. Okay, so you can say that the hot wire is fragile in nature. Okay, and they are not that strong. Okay, so hot wire instrument carries this fragile hot wire. Okay, the response time is slow and the sensitivity is also poorer. Okay, and they are affected by ambient temperature, and this is the biggest disadvantage of this hot wire instrument. Okay, and since we have seen that theta is directly proportional to I square rather than being proportional to I, means that it has a non-uniform scale. Okay, so these are some of the disadvantages of the hot wire instrument, but the application of these instruments are very vast, and that make it suitable for as an alternating technology to the existing moving iron and electrodynamometer kind of instrument. Like they can be utilized for high frequency AC measurement, say RF current measurement, calibration in the laboratory, for special industrial measurement, and also in the thermal converter. So there are a number of advantages of this hot wire instruments. Okay, so with this, I think the construction and working of this hot wire instrument is clear to you. Okay, so in the next class what we will do is we will talk about the thermocouple kind of instrument, and of course when we will talk about thermocouple, this is just about the analog instrument. Of course we will cover this thermocouple also in the next module when we will talk about the transducers, but I will give you a general overview of the thermocouple and thermoelectric effect. That will also help you when you will understand the next module, which is on transducers. Okay, so we will go like that. We will talk about the thermocouple itself first, and then we will talk about the thermoelectric kind of electrothermic instrument. Okay, so with this we have finished our discussion on the hot wire kind of instrument. Thank you.